This is 1.3, Part C, on linear relationships. So the first definition here is of modeling, which is the process of creating a mathematical function or equation that is a good representation of a real-world situation. It's not going to match exactly, but it does so closely enough to be useful for making predictions. In this section, our models will be graphs. In the next section, we're going to actually find equations for the models. In Unit 1, we're working with linear models. When we get to Unit 2, we're going to find other forms of models. Okay. So, example 8. A basement is flooded with water. We want W to be the amount of water in cubic feet that remains in the basement T hours after pumping. We've got some values listed here. Now, the amount of water in the basement is going to depend on the amount of time. So the amount of time has to be the independent. Usually, if you're given a chart like this, the independent values will be listed first, but it is good just to clarify, just to make sure that this makes sense, that the amount of water does depend on the time. Okay? So, the first thing I want to do is create a scattergram. So my independent value is 0, matches with 900 on the dependent. 2 with 700. 4 with 500. 6 with 300. And 8, 100. Okay. That's my scattergram, and we label these. I've got my T for time and W for the amount of water. Next, I want to draw a line that comes through all the points in the scattergram. So hang on a second, let me get my ruler. Alright, so I'm going to draw a line through all of the points on my scattergram. And this line itself is the model. Okay, so I've drawn the model. We're going to use this line or model to make predictions. First, let's fill in our definition. If the points of the scattergram form a straight line, then the two quantities from the real-world situation are said to be linearly related. The mathematical description or a scattergram is called the linear model. Okay. I'm going to get the next page, and we're going to use the scattergram that we draw in conjunction with the examples on the next page. So, in Part C, I want to use the linear model to estimate the amount of water in the basement after 3 hours. Okay, so after 3 hours, you can see that it looks like there were 600 feet of water. So I'm going to first write that ordered pair. That ordered pair is going to be 3, 600. That's the ordered pair that satisfied that condition. And the sentence means that after 3 hours, 600 cubic feet of water was left in the basement. Okay. In Part D, I want to use the linear model again to make another prediction. I want to predict when there was 200 feet of water in the basement. See our model. 200 feet of water. Trace it over to our model. Looks like 7 hours is going to match. So the ordered pair would be 7 for the independent, comma, 200. So we're going to have 7, comma, 200. And again, the explanation. After 7 hours, there are only 200 cubic feet of water in the basement. All right, another definition here. An input is an appropriate value of the independent variable that leads to at least one output, which is an appropriate value of the dependent variable. So continuing that water example, that basement water example from number 8, is 100 an appropriate input value? Look back at our chart, input values are independent values. So the independent values range from 0 to 15. 100 is not going to be an appropriate input value, specifically because after 9 hours, the basement is empty of water and you're going to stop pumping. So it's outside of the range of values that make sense. So this is going to be no. Okay. 100 is not an appropriate input value. The basement is empty after 9 hours. So 100 is outside the range of time values that make sense. Okay. Part F just asks us what values are appropriate for output. Let's look at our graph again. What values are appropriate for output? So it looks like 900 is the maximum capacity. That's what the basement originally held. And it's getting lower and lower and lower down to 0. It can't go below 0 because you can't have a negative amount of water in your basement. So anything between 0 and 900 is going to be acceptable. Okay, so appropriate values for output are values between 0 and 900 cubic feet. Okay, and again, some reasons for that is we know that we don't want any negative values. And we also don't want values that are too large. We also know that the basement had the most water. Was the 900 cubic feet. Okay. Definition on the bottom of my page here. The x-intercept of a line is the point where the line crosses the x-axis. Okay, so if your line is going to cross the x-axis, then it's going to have a y-coordinate of 0. It's going to be somewhere on the x-axis with the y-coordinate of 0. So the y-coordinate of an x-intercept is 0. The ordered pair would look like x comma 0. Similarly, if you're going to have a y-intercept, a point on the y-axis, then the x-coordinate that has to be 0. So this kind of point would look like 0 comma whatever the y value is. Turning our page. All right, we're going to continue with that water example. So we're going to look back at our model and find the w-intercept and the t-intercept. So the w-intercept is where the model crosses the w-axis. So the ordered pair for this is going to be the ordered pair 0 comma 900. The w-intercept should only have a value for w. The t value should be 0, and you can see that it is. What does it mean in this situation? It means that when you started pumping, that's at time 0. So when you started pumping, so parentheses, t equals 0, there were 900 cubic feet of water in the basement, or there was 900 cubic feet of water in the basement. Flipping back to the graph, I want to find the t-intercept. The t-intercept is where my graph crosses the t-axis. That's going to be down here at the ordered pair 9 comma 0. And this ordered pair means that after 9 hours, there is 0 water in the basement, or the basement is empty. So after 9 hours, there is no water, or 0 amount of water, 0 cubic feet of water left in the basement. Okay. I think we're finally done with example 8, that water picture we drew. We used it quite a bit. Example 9. We're going to consider the graph shown over here. And again, this is the line. You can see the x-axis, the y-axis, and I want to talk about a few points on this line. First, I want to find the x-intercept. That's the place where my graph crosses the x-axis. That's going to occur at 2 on x, 0 on y. So I'm just going to write down the ordered pair for the x-intercept. 2, 0 is where my graph crosses the x-axis. The y-intercept, right, here's my y-axis, where my graph crosses the y-axis is right there. The x-coordinate will be 0, the y-coordinate will be -1. So this is the ordered pair 0, -1. Find y when x equals 6. So 6 for x looks like y is 2, so I can just write y equals 2 here. And find x when y is -4. So -4 on y, trace it over to your graph. It looks like it has an x value of -6. So just about reading the graph, these two things, C and D, are something we've done from previous knowledge, but the new topics for this question are the intercepts. Okay, on to the next page. Example 10. The amount of money that Americans spend annually on cell phone services is growing. We want this function, m equals f of t, to be the amount of money spent on cell phone services at t years since 2000. Okay, so if I'm doing t years since 2000, I'm going to go ahead and fill my t values out here. This is going to be 1, 2, 3, 4, 5, 6, and 7. And I can see that these are already graphed for me. 1, 2, 3, 4, 5, 6, 7. If they weren't graphed for me, I can graph them myself. I have both the dependent and independent values. Okay. Now I want to draw the graph of a linear model. Again, that's a line on the scattergram below. Now this is going to be a linear approximation. These points do not line up perfectly like they did in our water example, example 8. So I'm not going to try to find the line that contains the most points. I'm going to just try to find some sort of middle, where some points are above and some points are below. I want my line to come close to all the points. It doesn't even need to go through any. Okay, so I'm going to try to cover up about half of them. Let's see if I can do this. If I had a clear ruler, it might be a little more helpful, but I'm going to give this a try. Okay, looks like I'm a little low. Let me see if I can get it to show up a little higher in black ink. Try a second try here. Might need a clear ruler to get any better. We'll go with that black line though. Yeah. So the black line, you can see there are a couple points above it, a couple points that are just a little bit below it. So this is going to be our model. I'm going to make that a little thicker. All right. So that's the model. You might have to use a pencil and erase a few times before you get it right, especially if your ruler is not clear. I'm going to use that model, that black line I've drawn up here, to make a couple predictions. And so in part B, what would the model, that's the line I drew, predict as the amount of money spent on cell phone services in 2000? Okay. So in 2000, that's the year t equals 0, since I'm talking about years since 2000. It looks like it's just above 100. So since that's 200 up here, just above 100 might be like 105. So we're going to make a guess for that ordered pair 0, 101, 105. That doesn't really matter. It's just a little bit above 100. So I'm not going to say 100 itself. Okay, so I need to make sure I write this in a sentence. That t equals 0 means in the year 2000. And then the result, about $105 is spent annually for cell services. All right. Part C. When would the model predict that people in the U.S. spend about $800 annually on cell services? So I'm going to use my model again, trying to find 800. 800 looks like it hits right here. Okay. So on the line for 10, it's a little bit above 800. 800 hits right in between 9 and 10. So in between 9 and 10, I'm going to go with a let's just say that's like 9.8. So we'll say a t-value of 9.8. So I'm going to write this as the ordered pair, 9.8, comma 800. But for the explanation, what year represents 9.8? The year for 9.8 is going to be the year 2009. It's definitely not 2010 yet, right? So if you think about over here being 2009, this over here, so 2009 is where 9 is, this over here is 2010. Even though I'm close to 2010, if it's November or December in 2009, it's still the year 2009. So anywhere in between these 2 points will be in the year 2009. You haven't reached January 2010 yet. So in 2009, 800 was spent on cell services, spent annually on cell services. Okay. Definition at the bottom. Interpolation is used when I'm making a prediction between 2 points that are already known, and extrapolation is when I'm making a prediction that is beyond 2 data points. Okay, so I'm going to label the areas of interpolation and extrapolation on the graph above. Okay. So anything in between data points, so in between first and last data points, is my area of interpolation. And anything outside the data points in either direction is going to be extrapolation. It's important to know whether your prediction is an interpolated prediction or an extrapolated prediction, because interpolation predictions are more reliable than extrapolation predictions. So both of the two that we were looking at were extrapolated. It's just important to think about when you're looking at any kind of statistic or data online. If it's in between data points, there's a better chance of reliability than there is if it's an extrapolated beyond the data points. All right, our section continues with example 11. The percentage of materials that are recovered for recycling are shown in the table for various years. Let P be the percentage of materials recovered at T years since 1990. So the first thing I want to do is list my T values. Since 1990, that's going to be 4, 6, 8, 10, and 11. I'm going to make the scattergram, and then I'm going to draw a linear model. So 4, 24, so just below 25. 6, 27, so just under halfway between 25 and 37, same thing, or no, 8, same thing. 8, 27 also. Then 10 is going to be 29, so that's just under 30. And 11, 30 itself. All right. So I need a ruler again to draw a model. And I want to try to hit the middle. So I'm going to have a little bit above and a little bit below. All right, let's see if I can do a good job with this. The ruler thickness is a little off. But let's see. All right, might be a little on the low side because I see a big space in between, but it seems to be fitting very close to all my data points. So it is acceptable as a model. All right, and I want to use this model now in part C to predict the percentage of materials that will be recycled in 2011. Okay. So 2011 is going to be the T value of 21, which you can get from taking 2011 and subtracting 1990. You should get 21. You can literally subtract on your calculator to figure out what your T value is going to be. Subtract your starting year. Okay, so 21, good thing I made my line go this far. 21 is right here, and that's probably 48. I'm sorry, 38. Not quite to 40. Probably about 38. So I'm going to have the ordered pair 21, 38. All right, so that means that in 2011, 38% of materials are recycled. I also want to point out that this is not the only correct answer. If you drew your straight line and it doesn't look like 38, but it looks like 40 or 36, your answer is still correct based off of your model. When we draw these models, are making a guesstimate. They're not as precise as in the next section when we're going to make an equation that describes the model. The aligned linear models right here are estimates, so it's okay to have a slightly different answer right here as long as it matches the model, the line that you drew. Part D. I'm going to use this model, the one I drew, to estimate when 33%, which is about 1/3 of materials, were recycled. So 33%, a little more than halfway in between. It looks like right here. Okay, so it looks like it could be in the year value for 15. So I'm going to have 15, 33. And the year 15, again, that's 15 plus my starting year of 1990 is going to be 2005. So in 2005, 33% of materials were recycled. The note on the bottom of the page is about errors in estimation. It's also common to confuse the meaning of data points and the points that lie on the model. For example, if I were to ask you what percentage of materials were recycled in 1996, according to the model 6, you would say 25, even though there's a data point stating it's 27. The model will not give you the same thing necessarily as any of the data points. Okay, so it's important to make your prediction based on the line that you drew, not based on the dots. Okay, and the error in an estimate is the amount by which the estimate differs from the actual amount. Right? So I think 1996 is actually part of the example on the following page. So we'll make that note. We're using the model to predict the number in 1996. And in 1996, it looks like 25. So it looks like P equals 25, but I know that it was actually supposed to be 27. So this is an underestimate. The model is below the data point. The error is going to be 27 minus 25, which is 2. Okay, so an error of 2 units, and the units in this case were percent, so 2 percentage units. All right, part F, new topic. What does it mean if P equals 100? Okay, so P again stands for percent in this model. My chart doesn't go up to 100, but if it did, P equals 100 would mean 100%, would mean all materials are recycled. So 100% means that all materials are recycled. And it's just good to note because we know that P can never be greater than 100 because you can't recycle more than 100% of the materials. So again, just thinking about what values are acceptable for the dependent variable, they have to be below 100. Okay, so no, P could not go above 100 because you can't recycle more than 100%. If it did, I'll make that note as well, can't have more than 100%. Oops. If you did make a prediction that went above 100% or some other thing that didn't make sense, that's what you say you have model breakdown. Model breakdown is when a model gives a prediction that makes no sense. This happens especially often with far extrapolated predictions. And our last example, example 12, consider the following scattergrams. For each, determine which ones are appropriate to use a linear model. So the first one, you can grab a ruler and you can quickly see that you would be able to draw a line going through or close to all those data points. So this one is linear. Okay, if you would not be able to draw a line in the middle of the second one, so this one's definitely not linear. It's got a nice curved shape to it, but it's not a linear shape. And the last one, these aren't a perfect line, but you could get a line that was fairly close to the data points, some above, some below. So this one is also linear. Okay, so there are two cases here, one that's very perfectly close to the straight line and one that's just a little bit more off, but they both have a general line type shape. So those are the types of data that we would expect to see in this linear modeling chapter. And that is the end of section 1.3.